Hello, and welcome to this lecture on Reynolds Chapter 3 entitled Concepts. Before listening to this lecture, you should have read this chapter. Again, we begin with Alexander's model and this depiction of the encoding process. The terms ideas and concepts have very similar meanings and are sometimes used synonymously. For our purposes, we will use ideas to refer to general concepts that have not yet been given an explicit description or definition, and concepts to refer to ideas that have been fully described or defined. Ideas can be vague, but concepts must be very specific. So if we look at Alexander's encoding process, does the C refer to ideas or concepts? The answer is both, because we often have ideas that seem to be lurking in the back of our minds, or we have a feeling about something that we can't quite put into words. It's like when we say, I just can't find the words. We have an idea about concepts and about things, but to become a concept that can be used in science, we must have the symbols or words to fully describe or define them. This chapter is all about concepts as they are used in traditional science, almost all of which applies across all three of the paradigms we are studying in this class. In this lecture, we will define concept, talk about the differences between abstract and concrete concepts, about the relationship between abstract and concrete operational definitions, about procedures for measuring abstract concepts, and about the quantification of theoretical concepts and operational definitions. Concepts require written language. A concept can't be used in science unless it is expressed in a natural or artificial symbol system, such as English or mathematics, or both. Expressing concepts in symbol systems allows for the transmission of meaning from one generation to the next. Perhaps more importantly, it allows for the possibility of developing agreement for the meaning of the symbols used to represent concepts. Traditional science categorizes symbols as either primitive or derived. Traditional science makes the distinction between primitive and derived symbols as a way to delimit meanings, as a way of zeroing in on the smallest and most immediate unit of analysis. Traditional science often uses mathematical notations to create something similar to algebraic formulations. The charts on the right of this slide indicate how this works. Here we see that the symbol X stands for the individual as a goal-oriented entity. Y stands for the interaction that denotes the presence in a social system. Z stands for two or more regularized cases, which denotes the existence of formalized rules and procedures. Each of these are primitive symbols. They cannot be broken down into smaller units of analysis. Derived symbols are created by the combination of primitive symbols into relationships. Again, mathematical notations help indicate the nature of these relationships. So we have the equation Z equals X plus Y. Thus, a traditional science researcher might begin their research with the concept that when two or more individuals interact regularly, we have a goal-oriented social system that is formally organized with rules and procedures. The effort in all of this is to limit the meaning of X, Y, Z, plus, minus, and equal to the greatest degree possible. The goal is to control the symbolic universe that humans live within so that it does not distort the external reality that traditional science seeks to study. This means separating aspects of the external reality into the smallest possible units, and these units of reality must function acontextually or across all possible cases regardless of context. Within the traditional science paradigm, derived symbols are more efficient because they group primitive symbols into sets of relations, and this allows for the examination of reality in larger units. This is, of course, an imperfect process because we are talking about human beings using symbols, which means that Alexander's problem of referent equivalency and the problem of added meaning, as noted by Reynolds, remains. In traditional science, the effort is to reduce everything to sensory impressions, or to make sure that all scientists are perceiving the same unit of reality in the same way or as the same thing. But when it comes to human beings, our sensory impressions or perceptions are always more involved than identifying an object of perception. Consider the sensory perception of having butterflies in your stomach. This can never be pinpointed except for each particular case experienced by a person within a given context who can say that they have butterflies in their stomach. On this point, it is worth taking another look at Reynolds' discussion of sexy girl. Reynolds' point here is that there is some level at which the concept sexy girl is impossible to pin down, that knowing what a sexy girl is a matter of just knowing because we share a cultural milieu. But beyond this point, there is also much to say about Reynolds' choice to use sexy girl as an example. I won't elaborate on this point here, but I think it is important to point out that our biases and prejudices can never be eliminated, and sometimes, as in this example, cultural prejudices serve as a very clear touchstone for mutual understanding. In cases like these, the effort to quantify our linguistic descriptions fail, whereas the social science paradigm seeks to limit these points of failure in research. The interpretive and critical paradigms feature them in research. The distinction between abstract and concrete terms is important across all three of the paradigms we are studying in this class. Understanding the distinction between abstract and concrete terms helps all of us be more precise in our meaning, not just in conducting research, but in our everyday communication as well. Abstract concepts are independent of a specific time, place, or instance. Concrete concepts, on the other hand, are tied to a specific time, place, and instance. Take temperature, for example. Temperature is an immediately felt physical reality that exists across all contexts. It is abstract in that it exists independently of a specific time, place, or instance. But if we talk about the temperature of the sun, now we have delimited the scope of the meaning of temperature. We have made it more concrete. We can make it even more concrete by specifying the temperature at Sky Harbor Airport on January 1, 2004. A social science example is the concept of emotion. All human beings experience emotion. As a concept, emotion exists across all instances of time, place, or instance. Emotion is a very abstract concept. Anger is more concrete than emotion because it is more delimited. Anger is an emotion, but not all emotions are anger. If, however, we talk about a raised voice that uses derogatory language, we might have something even more concrete. In the social sciences, these more concrete concepts are determined to exist by a trained observer or as measured by using a survey or a questionnaire. So we are always talking about degrees of abstraction, and in this sense we have two meanings of abstraction, as independent of time and space and as inclusive terms. Abstractions independent of time and space include concepts such as love or freedom. It is very difficult to make the idea of love or freedom concrete, except for those cases where people experience them. To study love or freedom in traditional science is very difficult because these meanings can be unless these meanings can be translated into observable behaviors that function across all contexts and cases. The second meaning of abstraction refers to inclusive terms, where one term is included in the other. We have examples of this in the previous slide. The temperature of the sun is included within the concept of temperature. The concept of anger is included within the concept of emotion. Similarly, the concept of liking is included within the concept of sentiment. In each case, the more abstract term includes the more concrete term. Once traditional science has disciplined itself to create symbols that can delimit the meaning of the concepts by making them more concrete, the next step is to create operational definitions. This step is key in allowing traditional science to develop hypotheses that can then be tested. Reynolds defines operational definitions as a set of instructions independent of time and place that describes what operations to follow if a concept exists in a particular situation. A similar definition is how variables are defined in a specific research study. Operational definitions allow us to determine when a concept is too abstract to be useful. When we study Zhang's work as an exemplar of the social science paradigm later in this course, we will see how the concept of self-construal and conflict style are operationalized as variables in the study. It is important to remember that several operational definitions may be indicators of a single theoretical concept, and a single operational definition may apply to several theoretical concepts. Once we have operational definitions, we have to put these into relationships. We do this through the construction of statements. A statement is a description of a relationship between two or more concepts. Relations are always abstract, but like concepts, have different levels of abstraction. Relations and concepts tend to be correlated at the level of abstraction, which means that if the concept is high in abstraction, then the relations that employ that concept will also be high. A theoretical concept is any concept more abstract than an operational definition, or more abstract than a procedure for measurement. That is part of a theory, or is potentially useful for inclusion in a theory. So let me say that again. A theoretical concept is any concept more abstract than an operational definition, or more abstract than a procedure for measurement, that is a part of a theory or is potentially useful for inclusion in theory. As scientists make these determinations about whether or not a concept, whether or not a theoretical or operational definition is too abstract or not, this is largely a matter of judgment. This means that the community of scientists play an important role in establishing the conditions of judgment. Once we have concepts and their operational definitions in place, traditional science proceeds through measurement. This is the key to developing empirical relevance, which is the key to how social science paradigms establish the validity of research results. Empirical relevance requires that it be possible to compare the statement to some phenomena or phenomena. This means that theoretical concepts should be related to the sensory impressions in concrete situations. In other words, it requires that our theoretical concepts should be connected to the specific instances of human perception. When we study the research conducted by Zhang and their colleagues later in the semester, we will see how the social science paradigm uses surveys or questionnaires as the specific instance of human perception that links to the theoretical concepts such as self-construal or conflict style. A hypothetical construct is a theoretical construct that cannot be measured in a concrete setting. Later in this course, we will study the work of Lee Pierce, and we will see how the critical paradigm uses theoretical constructs that cannot be measured in a concrete setting. The operational definitions are evaluated by two criteria. First, how strongly is its relation to the theoretical concept? And second, how suitable is it as a measurement procedure? Both of these require intersubjective or inter-observer agreement. This agreement is concretized by checking if two or more properly trained observers arrive at the same result if they follow the same procedure. Perfect agreement is difficult to achieve, therefore an arbitrarily selected degree of agreement is required. Here are some examples of measuring concepts as used within the social science paradigm. Let's say we want to do research on anxiety or conflict style. We might use trained observers to observe people interacting in a laboratory situation, or use physiological measures such as heart rate, skin temperature, etc. Or we could use a questionnaire which asks research subjects to self-report about their experience of anxiety or conflict. Another example is measuring one's status within a group, or the existence of a power hierarchy within a group. These might be concretized as the volume of voice or frequency of speech by who initiates speech to others and who is subjected to speech by others. This can be judged by trained observers or reported by group members themselves, or as compared to one's speech behavior as it occurs in private, outside of the influence of the group. It is important to remember that different ways of measuring often results in different degrees of correlation. So if one study uses trained observers, but another study uses questionnaires, even if the same operational definition is used in both studies, any differences in correlation may be the result of the measurement instrument itself. Another potential problem is that the meaning of the concept as understood by the research subjects may not be captured by the operational definition. As research subjects, we experience this in reality when we are given a questionnaire that requires us to select one of a number of possible answers, and we think to ourselves, well, none of these apply. Once we start using operational definitions and statements that can be tested as hypotheses, we have three possible relationships established. The first is a positive correlation, where one is high and the other is also high. This positive correlation allows us to continue working with the established operational definition. The second is a negative correlation, where one is low and the other is low. A negative correlation suggests confusion in the operational concepts and perhaps the theoretical concepts as well. This result suggests that new theory development is required. The third relationship is where there is no correlation. A lack of correlation suggests inadequacy in the theoretical or operational aspects of the concept. In this case, researchers must go back and reconsider the operational definitions they are using. Beyond having a positive, negative, or no correlation among operational definitions, we also have ways of measuring these correlations. We have four types of quantification, or levels of measurement. Nominal quantification refers to discrete states that bear no relationship to one another. This is a standalone quantification that can be measured by any label, whether linguistic or numerical. You could say thingamajig or whoop-de-doo. Ordinal quantifications involve states that can be rank ordered with no indication of differences between orders. For example, consider the relationship between a seedling, a sprout, and a plant. At what point exactly does a seed become a sprout and a sprout become a plant? It's very difficult to identify a specific point at which we have one moved from one stage to the other. Interval measurements involve ranking each state where the difference between each is the same and without a zero. Consider the sequence of 16, 19, 21, 24, 27, 30. Clearly, this is a count of 3 between each number, and that would continue throughout the sequence. The last type is a ratio measurement. Here, the presence of 0 allows intervals to be calculated as ratios. Consider this sequence: -3, -2, -1, 0, 1, 2, 3. The presence of 0 allows us to fix a specific ratio between two things. In general, quantification allows social science to manipulate variables and make a judgment about the existence of the phenomena. Numbers allow for quantification in ways that are fixed and not subjected to the added meaning problem. Quantifying theoretical concepts is much more difficult than quantifying operational definitions. Quantification can also allows for more precise statements to be made about the degree of association among concepts. As useful as quantification is, it is important to remember that quantification is not in itself an indication of scientific knowledge. It is unfortunate that people often think that if something is represented by numbers, it makes it scientific. Reynolds makes this point exactly and emphasizes that the development of quantitative measures, operational definitions, and so on must be put into conversation with a community of scientists to achieve the status of being scientific. This lecture has focused on the role of concepts in the scientific process. We have defined concepts, addressed the relative levels of abstractness and concreteness of concepts. We've discussed the relationship between abstract concepts and operational definitions and the procedures for measuring abstract concepts, and the quantification of theoretical concepts and operational definitions.